Operations Research, Week 1, Wednesday. First, it starts by giving that you can recommend supplemental reading by reading Chapter 3 of Winston's Operations Research text. And then we go through two definitions. The first is, if any linear programming model, the decision variables should completely describe the decisions to be made. Second definition, if any linear programming problem, the decision maker wants to maximize, usually revenue or profit, or minimize, usually costs, some function of the decision variables, the function to be maximized or minimized is called the objection function. First example of Wednesday. Oh Boy Toys, OBT, manufactures two types of wooden toys, soldiers and trains. A soldier sells for $5 and uses $1 worth of raw materials. Each soldier that is manufactured increases OBT's variable labor and overhead costs by $1.50. A train sells for $4 and uses $2 worth of raw materials. Each train built increases OBT's variable labor and overhead costs by $1. The manufacture of wooden soldiers and trains requires two types of skilled labor, carpentry and finishing. A soldier requires 2 hours of finishing labor and 1 hour of carpentry labor. A train requires 1 hour of finishing and 1 hour of carpentry labor. Each week, OBT can obtain all the raw materials needed, but only 100 hours of finishing and 80 carpentry hours. Demand for trains is unlimited, but at most 30 soldiers are bought each week. OBT wants to maximize the week's weekly profit, revenues minus costs, formulate a mathematical model of OBT situation that can be used to maximize OBT's weekly profit. So first we form the objective function. It is a maximization, as it is told here. So we have z equals, we have to combine a few different variables here. So it's 5 minus 1 minus 1.5, and this is for x1, which I labeled over here as soldiers. I should have done this first. x1 in these problems is soldiers, and x2 is trains. So I said first for x1, we go through and find everything for the soldier. We have $5, $1, and 1.5. Those have to be subtracted from the $5, and you get a $2.5 profit. For x02, it is $4, using $2, and using $1. So it's 4 minus 2 minus 1. So it's a $1 profit. And this is your ISO profit line. Next, we find the subjects, which is our constraints. So we have the carpentry constraint, which means we only have 80 hours of finishing. We have the of carpentry. We have the finishing constraint that only has 100 hours. The demand of soldiers, which is 30 a week. And of course, our non-negativity constraint, which means that x1 and x2 have to be greater than or equal to 0. So then we add our constraints to our graph to solve it graphically. Here's our feasibility range, and here are our 5 points, 0, 0, 30, 0, 30, I'm going to assume that's 40 there, probably a little off, and then we have our, I'm sorry, I can't read the numbers on my graph, I'm assuming that's 35, 60, and then 0, 80. Plugging in to solve, we figure out that the best profit is at 30, 40, with z equals 115. Excuse me if you hear noise in my background. My roommates just started watching a movie or something. Next, we move into a definition of linear programming problem, which is LP. An LP is an optimization problem for which we do the following. First, we attempt to maximize or minimize a linear function of a decision variable. The function that is to maximize or minimize is called the objective function. 2. The value of the decision variables must satisfy a set of constraints. Each constraint must be a linear equation or linear inequality. 3. A sign restriction is associated with each variable. For each variable xi, the sign restriction specifies that xi must be either non-negative, xi must be greater than or equal to 0, or a restricted sign, URS. Definition 1.25. The feasibility range for an LP is the set of all points that satisfies all the LP's constraints and sign restrictions. Definition 1.26. For a maximization problem, an optimal solution or optimal basis to an LP is a point in the feasibility region, with the largest objective function value. Similarly, for a minimization problem, an optimal solution is the point in the feasibility region with the smallest objective function value. Wow, words are hard. Okay. Model LPs have only one optimal solution. However, some LPs have no optimal solution, and some LPs have an infinite number of solutions. Finding the optimal solution. Having identified the feasibility region for the oh boy problem, we now search for the optimal solution, which will be the point in the feasibility region with the largest value of x equals 2.5x1 plus x2, which we found before here as our objective function. To find the optimal solution, we need to graph the line at which all points have the same z-value. In a max problem, such a line is called the isoprofit line. In a min problem, an isocost line. To draw an isoprofit line, choose any point in the feasibility region and calculate its z-value. All isoprofit lines have the same slope. This means that once we have drawn one isoprofit line, we find all other isoprofit lines by moving parallel to its isoprofit line we have drawn. Definition 1.27. A constraint is binding if the left-hand side and the right-hand side of the constraint are equal to the optimal values of the decision variables are substituted into the constraint. I'm sorry, reading these notes right now is really hard for me. Now we have a question. So which of the constraints on the oh boy problem are binding? Referring back, this is the problem. After looking at that, we know the constraints that are binding are x1 is less than or equal to 30, and 2x1 plus x2 less than or equal to 500 is binding. So which constraints are non-binding? x1 plus x2 is less than or equal to 80, because 30 plus 40 less than or equal to 80 is 70, so it has a slack of 10, which means it's non-binding. Let's see what happens when the market forces change in our objective coefficients. Example 1.28. Things have changed for Oh Boy Toys, OBT. Due to limited demand, a soldier now sells for $4 and uses $1 worth of raw materials. Each soldier that is manufactured increases OBT's variable labor and overhead costs by $1.50. A train sells for $6 and uses $2 worth of raw materials. Each train built increases OBT's variable labor and overhead costs by $1. The manufacture of the wooden soldier trains requires two types of skilled labor, carpentry and finishing. A soldier requires 2 hours finishing labor and 1 hour of carpentry labor. A train requires 1 hour of finishing and 1 hour of carpentry labor. Each week, OBT can obtain all needed raw materials, but only 100 finishing hours and 80 carpentry hours. Demand for the trains is unlimited, but at most 30 soldiers are bought each week. OBT wants to maximize the weekly profit, revenues minus costs, and formulate a mathematical model of OBT's situation that can be used to maximize OBT's weekly profit. So again, we start with the objective function, which is a maximization function, and we have z equals 4, minus 1, minus 1.5. Oh, and again, x1 is soldiers and x2 is trains. Almost forgot that again. And then for x2, we have a train is 6, minus 2, minus 1. So our new objective function is x equals 1.5 x1 plus 3 x2, and that is our isoprofit line. We go down to our constraints, because our equation is subject to carpentry, which is x1 plus x2 is less than or equal to 80, to x2 plus 2x1 plus x2 is less than or equal to 100. And then, of course, our constraints for soldiers, which is x1 is less than or equal to 30 because it has to be at most 30 bought each week. And then our non-negativity constraints, x1, x2 is greater than or equal to 0. Going down to our graph to solve the problem, we do our constraints, which are the solid black line. The dashed line is the feasibility region. This is our isoprofit line, which means right here is our greatest answer because it's on the isoprofit line and it's in our feasibility region. So our equation at 0, 80 will give us 240. And that is the end of week 1 Wednesday.